Hello and welcome to the first lesson of Unit 7 Exponential Functions in our Grade 11 University College Math class. So I'd like to start by saying that this unit in particular was designed to fulfill the specialist high skills major requirement at our school. So a lot of the lessons in this unit are different than they have been in the units that precede it, in that they're sort of a little more interactive, and the topics that we're going to be investigating, they tend towards health and wellness or sort of like information and technology, like tech. So those are the two sort of branches, the two specialist high skills major for which this was designed. They don't necessarily make for the most repetitious lessons in terms of practicing what we learn. So I'm hoping that they work out pretty well. I didn't want to just throw a whole bunch of new lessons at you because most of you already had these notes in your possession. So without further ado, let's jump into this unit on exponential functions, and we're going to start with exponential growth. So a common place that we hear exponential growth is in the field of health, and actually at this very moment the spread of disease is what is resulting in us making these video lessons so that because we can't be in school right now because of this spread of a very infectious disease. So this is, when we usually do this in class, this is kind of a fiction or it's sort of imaginary. At this moment it's very real and actually a little bit scary. So this is one of those cases where the math that we're doing has a real world relevance. So let's start with the spread of disease question in part A. So it says you and a friend are infected with a particularly nasty and virulent cold, but you are determined to go to a party tonight. No social distancing. This cold is so infectious that when you touch someone, they are most likely to get infected too. Let's assume that both of you sneeze on, cough on, shake hands with, hug, high five, share a drink with, or smooch someone at an average rate of 2 people per hour. What will the viral transmission look like at this doomed party? So normally I have students in the class stand up and then they go and touch another 2 people, and then we count how many people there are. So unfortunately we're not going to be able to do that, but let's try to imagine that in our head. People standing up in our class full of 25 or 30 people, and then we would go out and touch people. So hour 0, when those 2 people arrive at the party, there are only 2 people who are infected, the 2 people who are arriving at the party. So at hour 0, that's sort of our first check-in, and then we are going to carry this all the way up to 5 hours. So if we'd consider that at 0 hours those 2 people arrive, and then those 2 people go out, they are in contact with other people at the party, each of them connects with someone else at a rate of an additional 2 people per hour. So I guess the way that we would just sort of sketch this, just so we can understand it, is here are our 2 infected people, and each of them go out and infect 2 more people. Visually, normally we would see this in the class. So if we count up the number of infected people, we have 1, 2, 3, 4, 5, 6. We have 6 infected folks happening now. And then another hour goes by. So now each of these 6 people is going to infect somebody else. So I'm going to do a little bit more sketching here. So this 2 more here, 2 more here. Now this person has 2. And this person has 2, and this person has 2, and this person has 2, and now we would count up all these people. So in hour 2, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 people who are infected. 18. Now it's going to get a little bit cumbersome to continue to make that type of drawing, but again, if you can imagine that, I think the part that people tend to forget is that while this person, one of our original 2, infected 2 people in the first hour, they did also go on to infect 2 different people in the next hour, and they themselves were also infected. Now we're going to start to see a pattern developing here, and students normally do. We see that the numbers here are going up. So how did we, in our table, how did we go from 2 to 6, and how did we go from 6 to 18? And we can see that this is going up by multiples of 3. So what you would have is 54 people infected in the next hour, 162 people infected the hour after that, and 486 people, which is quite a large party, I might say. Okay, so we've filled out our table. Now to figure out what type of relationship this is, what type of growth this is, we're going to do first and second differences. So we're going to fill these out. As you know, first differences would be the lower value subtracting the higher value in terms of their position on the table. So 6 minus 2 is going to give you 4. 18 minus 6 is going to give you 12. etc. So we're going to work our way down the table here. I'm going to do these on my calculator because I want to go really fast and not make any mistakes. So that's going to give us 54 minus 18. That's going to give us 36. And 162 minus 54 is going to give us 108. I'm going to just start writing some answers here. And 486 minus 162 is going to give us 324. So what do we notice from our first differences? Well, from our first differences, we notice that it's not constant. So what this tells us about this particular type of growth is this tells us this is nonlinear. We know that it is not going to be represented by a straight line. Now, we don't know anything else at this point. This is sort of our grade 9 learning, and I usually say that the thing we learn in grade 9 is that is something a straight line? If it's not a straight line, other. And then in grade 10 you get, if it's not a straight line, maybe it's a quadratic. That's where our second differences come in. And if not a quadratic, other. The third category, which we add here in grade 11, is if not linear, if not quadratic, possibly exponential. So that's what we're driving towards here. So now let's calculate our second differences. And as before, our second difference is the value lower down. Whoops, looking for a highlighter. Value lower down minus the value higher up. So that will be 12 minus 4, which gives us 8. And that will be 36 minus 12, which gives us 24. And we're going to keep working down the table. You grab your calculator, I'll grab mine. Let's see what we get. So we got 108 minus 36 gives us 72. And we have 324 minus 108. It's going to give us 216. So the values for our second differences are also not constant. So what does that tell us about what this type of growth this is? At this point, we know it's not quadratic. Not quadratic. Now again, just because it's nonlinear and just because it's not quadratic, it doesn't mean that it's exponential. We can't automatically assume that. We need to do a further calculation. So this is a new calculation for us. This is a ratio of y values. And a ratio, as you know, is one number over another, which is division. So I'm going to grab a new color, and we're going all the way back to our original table of values here. So we're looking all the way back over here. That's going to be 6 divided by 2. So going all the way back, 6 divided by 2. The next one will be 18 divided by 6. The next one will be 54 divided by 18. And then I don't remember the rest. 162 divided by 54. And last but not least, 486 divided by 162. And we're going to run all of these calculations through our calculator. Now the first few we can do off the top of our head for sure. 6 divided by 2 gives us 3. 18 divided by 6 gives us 3. 54 divided by 18 gives us 3. You might need your calculator for these last two, but they will also equal 3. So here's what we have. We have constant y ratios. And again, a ratio just means division. It's one number over another equals exponential function. Okay. So let's build an exponential function. That's the next thing we look at here in our lesson. So we're going to go in and fill in this table. Again, what we have here is we're going to try to model this situation with an equation. We're going to try to build it from scratch. So we're going to let n represent the number of infected people at the party after. So the two variables we've introduced here are n and t, n for total number of infected people, and t for time as measured in hours. So I've already filled in our table, 0, 1, 2, 3, 4, 5. That's the number we've looked at in our previous table. So in expanded form, what we ended up having, if we look at the very beginning, was actually, when we first got to the party, it was 2 people. So there's 2. And when 1 hour had gone by, we had 6 people, which interestingly enough is 2 times 3. And after 2 hours, we had 18 people, which is 2 times 3 times 3. So I think you're starting to see a pattern here where the number of hours that has gone by corresponds to the number of times we multiply by 3. So if we're going to continue that pattern, the third hour would be 2 times 3 times 3 times 3. The The fourth hour would be 2 times 3 times 3 times 3. I feel like I'm saying that a lot. And the last one is 2 times 3 times 3 times 3 times 3 times 3. Okay, so consider that we've written these in an expanded form. How would I now write these in an exponential form? Well, let's start with this last one. So this last one is 2 times, and there are 1, 2, 3, 4, 5 3's. So I might write that as 2 times 3 to the exponent 5. And the one above it, I would write as 2 times 3 to the exponent 4. And the one above it, 2 times 3 to the exponent 3, 2 times 3 to the exponent 2, 2 times 3, and again, we can write 3. I'm going to write 3 to the exponent 1 just to kind of keep the patterning going on here. And last but not least, 2 times 3, and we just learned this in the last unit. If I set, or continue with my pattern here, and I have 3 to the exponent 0, that's going to be equal 1. And 2 times 1 will give us 2, which is the number of people at the start of the party. So the equation that we have looks like, and let's write this in exponential form, where we have the number of infected people at the party equals 2 times 3 to the exponent time, the number of hours. Because again, that's sort of the piece that I'm hoping that we see here, is that number of hours that's gone by corresponds to the exponent that you're seeing in the exponential form that we're using to model the spread of this disease. So let's define our variables here. Let's let n represent, I'm going to write this short form just to save a little bit of time, number of infected people. T represents time, and that's going to be in hours. That was given to us in the question. Now the 2 here is going to represent what I'll call the initial amount. And that's the initial amount of people in this case. That's what we're talking about. And there were 2 people who got to the party sick. That's them. And the 3 represents the growth rate. And that's going to be tripling. It's going up. It's multiplying by 3 each time, and we call that a growth rate. So we're going to head down into the second part of this note, and yeah, I'll see you there. We're going to talk just a little bit about more how to make and then use these exponential functions.